Hello. Today I'm speaking to Kim Johansson, who is a PhD student working on the EiCLaR project. So welcome, Kim. And Kim is working in the Waste Science and Technology Division of Geosciences and Environmental Engineering at Luleå University of Technology in Sweden. So Kim is working on Work Package 3, which is all about enhanced phytoremediation. So thank you very much, Kim, for giving up your time for recording this podcast. I would like to start this podcast by just asking you to tell me a little bit about yourself.
Yeah, well, first of all, thank you for having me. I'm very pleased to be here. My name is Kim Johansson. I'm a PhD student at Luleå University of Technology, as you mentioned. I have been here for about 3 years now that I've been working as a PhD student and in this EiCLaR project.
And so how did you, with your PhD, have you done your undergrad at Luleå or have you moved to Sweden specifically for this project?
I'm actually from Sweden. I'm from Gothenburg in southwest Sweden. And that's also where I did my bachelor and my master.
So what did you do your Bachelor of Science in?
Well, actually, I have 2 Bachelor of Science, one in chemistry and one in environmental science.
Wow. And are they both three-year degrees? Is that?
Yeah.
Gosh.
And then I did my master in ecotoxicology. So all of that education I did in my hometown, Gothenburg, so the Gothenburg University.
Is that quite a common thing to do in Sweden, to do multiple degrees back to back?
Not really. Maybe I was just curious or a bit nerdy, I guess.
No, absolutely. It's just fascinating to understand how people end up where they are. Some of the other people on the project have also done multiple degrees. That's not very common within the UK, but that's from my perspective. So it's always interesting to know how people reach where they are. And so then you wanted to continue on to further studies with your PhD.
Yes, that was actually my plan, like since childhood, really. But in between, I had a few years in the industry because I feel like that is important also to have that perspective.
Yeah. No, absolutely. You have the understanding of what the problems are from the end user to.
Right.
So that's fascinating. So you've gone through education. Did you work in consultancy or did you work in where did you work in general?
I work in environmental consultancy, for example, at one company, and I also worked at an architectural firm with environmental issues. And I worked for the municipality at the waste company also.
Oh, right. So you've got all sorts of experience.
Yeah, exactly. Yeah.
And then you've gone back to academia to do your PhD. Gosh. So with your PhD in Sweden, how long are PhD normally? Are they 3-4 years?
Normally they are 4 to 5 years.
Are they?
Yeah.
So you do
it for quite some time here.
Yeah. So you do your research first, and then it's the writing. So the research element is 4 years, is it? And then the writing up, or is that included?
If you do a PhD for 5 years, it's then 20%. So 1 year is institutional work, it's called. So it can be teaching, for example. Or for me, I'm involved in the employment board here at the university. So it can be different tasks of that sort. And the other 4 years, there is a mix of, conducting research, writing, going to conferences, also taking courses.
So do you do any teaching as part of your PhD within the university? Do you help with any of the teaching? No. It's quite interesting. In the UK, often some of the people who are doing PhDs will help with the younger students in their lab area or something. So it's all quite, always very different and interesting how different institutions work. Yeah. So you're now up in the northern part of Sweden.
Exactly.
Where it's very cold.
We had -15 yesterday.
Wow, that
and is. It's gonna get colder,
Yeah. So it is it is very interesting. You are working on a work package to do with phytoremediation.
Yeah.
Now, phytoremediation, what is phytoremediation in simple terms?
In simple terms, well, phytoremediation is a remediation technology where we use vegetation to remediate soil. And traditionally, this was done by plant uptake of metals from the soil. So basically, you're just using the normal mechanism in plants, which is to extract soil water with nutrients. But we use it to take up contaminants instead. But it can also mean, for example, stabilization of contaminants by the root system or degradation of organic contaminants.
So plants they can be a really useful mechanism for remediation. So cleaning up soil, which is another term, or helping stabilize so those contaminants won't move off the site.
Exactly.
And impact other areas. Is there an issue with, you're obviously demonstrating phytoremediation, but you're in a very cold climate up in Sweden. That must have its challenges.
Yeah, of course. I mean, the summer here is 2.5 months maybe. So there is like a limited time of the season where plants can grow here. But that is also like the reality with the contamination, that we have contamination worldwide and we have different climates, and we have to adjust according to that.
Yeah, no, absolutely. So those areas that may be a lot warmer, that has its challenges in itself as well for growing certain plants in certain environments. So you're trying to understand the performance envelope, the breadth of different plants in different environments, trees, etc., that can help enhance remediation. So with this work package, you are what we're calling enhanced phytoremediation. You're adapting an existing technology. What does that entail?
Yeah, you could say that this enhanced phytoremediation is really a combination of different remediation technologies and optimization of them individually to create a greater remediation effect, a synergistic effect. And if I'm going to go a bit more into detail, then I might have to explain some concepts. So we already talked about phytoremediation in short and what that is. And we want to combine this phytoremediation with other remediation technologies, for example, with bioremediation. So that is where we use microorganisms in the soil to degrade contaminants. And that actually also just means taking advantage of their natural metabolism, because there are microorganisms that can use some organic contaminants as a source for energy and as a carbon source also. And in addition to that, we want to combine the phytoremediation and bioremediation with electrokinetic remediation. So this means remediation with electrodes that we insert into the soil. And traditionally, this electrokinetic remediation has been used to transport metal contaminants through the soil matrix, making them move towards the cathode, since they have this positive charge. And there at the cathode, they are being pumped out and they are treated ex situ. So that means away from the contaminated site. But this is a quite energy demanding process, and it also requires chemical additives to make these metals soluble so that they can move in the soil water. But here, and this is an example of the optimization, that instead of transporting the contaminants, we have set up the technology in a way that we can degrade or stabilize the contaminants depending on the contaminant type. So this means that the technique is a lot less energy demanding, and also that we can perform the remediation, but in a way that doesn't require chemical additives. So in this work package, what we wanted to do is to combine all these three, the phytoremediation, bioremediation, and electrokinetic remediation, and to see if that could have an increased remediation effect, as well as optimizing them individually. So when we say, for example, enhanced, we could mean exploiting the interactions between plants and microorganisms, or the stimulation of microorganism communities that can occur under this electrokinetic treatment. So in other words, it's about creating that positive feedback system so that these technologies are not only combined for a greater remediation effect, but in a way where they also all enhance each other.
That's fascinating. So again, we're looking at creating a toolbox, an optimum toolbox that people can use depending on the types of contaminants they have, and they will be able to identify what could work in combination. So we're trying to advance our knowledge on all of these different technologies and what we can combine together and optimize for remediation, for the improvement of the environment.
Yeah, and I think this work package is a lot about that, like optimizing, combining, but also like try to move from this lab scale proof of concept into real industrial scale implementations. And I think that's something very important. I mean, as researchers, we tend to look into details very much, and that is also important, but sometimes we dig and we end up in this bubble, and that's just one of the things that I like about the EiCLaR project, that it is a collaboration between university and industry, and that can help us break out of that bubble a bit so that we actually can implement these ideas and technologies as well.
Because for this project, as we would know from earlier podcasts, we have quite a number of industrial partners who have real sites that have contamination on them. So bringing the researchers' knowledge and expertise onto real sites is a novel aspect. And particularly for phytoremediation, can be perceived to be a very slow remediation methodology, can be more of a polishing technology, because using plants and trees and can actually be quite slow growing, and so extracting can be a problem. But with this work package, which is enhancing it, you're looking at the performance and combining it, which is the novel aspect, which is really interesting. So what would you say are generally the main challenges for this technology and this aspect of the project?
Well, as you mentioned, phytoremediation does require some time. It takes time for plants to establish and for the root system to develop. It also works best on low concentrations of contaminants and on shallow contaminants, because the remediation in general goes as deep as the root goes, or a bit deeper. But so there is a limitation there. But that is the thing with this project, that by combining different technologies, you can use them in a way that they complement each other.
No, absolutely. And that's, again, understanding the contamination on a site and understanding what would be suitable and what wouldn't be suitable. And that's all about developing the knowledge about your contamination, where it is, and what type of contaminants as well, because not all technologies can be used on all contaminants. So it's understanding which would be suitable. So again, it's this big toolbox and understanding what is suitable and what's not suitable. But you as researchers are trying to improve the performance of those technologies and extend the understanding of those, which is great.
Exactly. And to find these overlaps where they can actually enhance each other. So, for example, phytoremediation, as I mentioned, is more suitable on contaminants of low concentrations. And in fact, if plants are being introduced to heavily contaminated soil, they might actually die. So what we can do here, for example, is to start off with the electrokinetic treatment, and then after some time of remediation, plants can be introduced. And electrokinetics, on the other hand, has been shown to be more efficient on sandy soils than peaty soils, but many plants grow very well in peaty soils. So in that way, these technologies can complement one another, and we can have a greater remediation effect overall, hopefully.
Yeah. No, and like you say, different types of soils, which creates different
Yeah.
from different geologies. And again, I'm guessing pH for different types of soils can have an impact as well. And it's not my area, but I'm guessing with phytoremediation there are different plants for different types of contaminant that work better in different types of contaminants.
So overall, it's a very complex question, and I mean, you mentioned that it depends on the site and on the contaminant and geological condition and heterogeneity of the soil. I mean, there are a lot of things to consider, which makes it not so easy actually. But so this is the situation that we're faced with today.
Yeah. So whereabouts are your trial sites that you've been trialing the technologies on? Are they in Sweden?
So we have done experiments on different levels. So we've done experiment on lab scale, and then like an intermediate level between lab and field scale, and we also have a field scale implementation, and that we have in a place called Limmared in southern Sweden, and also our French business partners are doing their things in France. So,
so you're bringing the knowledge together between the two, which again is really, and they're a consultancy, I believe, the French partners. Yes. So it's bringing that knowledge again together from practical implementation from the academic research side, which shows the true partnership of this EiCLaR project, which is great. So if you had a magic wish ball, as we would say, and you coming from, you've seen the academic and you've seen the consultancy background, what would you like to see the next stage of this technology?
Well, the best thing, of course, would be if we stopped polluting the soil and groundwater. If I had a magic wand,
Yeah, a magic wand, yeah.
But other than that, I think like the next stages or the challenges that lie ahead of us is, for example, if we talk about this degradation of organic contaminants, of these hydrocarbons, we need to make sure that when we degrade them, that the degradation products are harmless or less toxic than the mother contaminant, for example. And another thing, when it comes to metals or metalloids, we have seen that with the redox-dependent metalloids, such as arsenic, the bioavailability is dependent on the redox potential. So that is a factor that is important to control in order to ensure that these contaminants are long-term stabilized in the soil. It's the tendency for chemical species to gain or lose electrons, so to speak. So it's about the state that the arsenic is in, and its toxicity can differ, for example, dependent on that and their bioavailability.
So they're available, to be broken down. So long term, we're looking to not continue to pollute, hopefully, and we have legislation to tighten that up, but we have a history, a global history of industrial contamination from processes and procedures that have happened in the past. So
actually, I mean, we have legislations, environmental legislations that are helping us, but there are also those that hinder us. And for example, today, how soil remediation is done is dig and dump or pump and treat, and that basically means that we dig up the contaminated soil, we transport it, and we dump it at the landfill, and then we call that soil remediation. Even though it's not really economical or environmentally sustainable. I mean, all these heavy transports emitting greenhouse gases, and on top of that, we need to mine for new and non-renewable material to fill up the hole in the ground, basically. So I think this speaks for development of soil remediating techniques that can be applied in situ. So that means like without excavating the soil.
Yeah. And that is something very much from a UK perspective, I can say that because we're a smaller island, much smaller than Sweden, we have, it is very expensive now to landfill soil. in situ remediation, that doing the remediation on site has grown. That side of the industry has grown hugely because of the costs, and we now have the sustainability aspects, as you mentioned, the carbon impact of digging up material, taking it off to landfill and putting the problem somewhere else is not necessarily the sustainable option, whereas something like phytoremediation, you're keeping the contamination. All of the technologies you were talking about working together collectively will keep that contamination on the site, and that will help the sustainability aspect as well, which is important, as long as you are protecting the environment and containing that contamination from going off site and maybe the impact of a watercourse or groundwater, etc. So it's a really fascinating area of research, and it's something that I think will grow. And if you've got large swathes of low level of contamination, I can see huge benefits of phytoremediation to help bind those contaminants and to stop that contamination going off site. So large mining sites, I think, are going to start looking at phytoremediation in a very active way, and combining it, I think, is a really exciting area of research. So I'd like to thank you, Kim, for your time and sharing your knowledge and expertise, and we will look forward to seeing the results of your research. So thank you very much.
Thank you so much, Nicola, for having me. It was a pleasure.
Thank you.